Hello everybody, and welcome to the Compilers Reading Group. This week's a bit special. Instead of having something to share and for everyone to read, I decided I'm going to cover JonesForth and kind of describe the implementation of JonesForth. Some interesting notes about JonesForth. The entire implementation is in this one-line assembly file. I'm recording this right now. It's being recorded as we speak. It's covered in this file, and it says 2,000 lines, but in reality it's about 700 lines of code. It's mostly comments. It's 2/3 comments. And Forth is kind of a special language. If you can imagine, it's 700 lines to implement like the base language and get up to speed. In reality, you can do it in like less than 400. But there's some interesting facts about Forth. Forth is a very interactive language. Down here in the bottom right, you'll see I have JForth open. And JForth is kind of nice. I can write definitions like double. It's a stack-based language for those who do not know. They should be used. And so basically, you have a stack. Dupe duplicates a thing off the stack. So if you have 5 and we dupe it, there's 2 of them. So the definition of double is just, well, we dupe the thing and we times it by itself. And as you can see, if we double, we get 625 and 9,000 period prints. There's other definitions we can do. We can start composing words that we just made. Yes, admit. There is some other fun things that we can do, like the word triple. I think I'm spelling triple right. Triple, is very similar in that it takes a word and you just double. Dupe the word and double. Let's just do dupe double times. This is probably wrong, but why not? And so Forth is quite flexible in this, in that you can just kind of compose words and things fall out. But what makes it so powerful is that it can kind of write itself. And I'm going to give you a little sneak peek before we actually get into the main compiler. There is some tricks we can do. Like I can just dump the memory address of any function, right? So if I push triple to the stack and I offset it by 5 cells, and I dump 8 cells, then we can actually see its memory layout, and this allows us to do a lot of powerful things. But before I get there, I'm going to show you kind of how JonesForth is implemented. We'll be using JForth for demonstration purposes, but it is effectively exactly the same. So JonesForth is written in assembly, and it's mostly text like this. But the interesting thing is kind of seeing how Forth is set up. So I want to show you the memory model first. The way that a lot of Forths are set up is that you have a link word at the front, and this is the language's dictionary, right? Like you can imagine that you need a dictionary of words, and the way that you store that is just a linked list. So you just have a coulter that goes to the previous word. And so when you find a new word, it just adds a new thing on latest. And we can actually just grab latest. It's triple. This thing says latest here, and we can just see that it's triple, the thing that we defined, which is quite nice. And then usually you store the name with some padding and the length. This is implementation specific detail, but that's what this name is right here. And you can see here, even in this Forth implementation, you see the word triple right here. There it's padded by 2 spaces, 2 20s, and then the word triple, which is 6 characters long. This is stored in what we call a cell, which is 1 word. And so that's kind of nice. We can kind of actually see from this the actual definition kind of in plain view. This is kind of important because everything is really simple, and it is very nice. And so when we talk about implementing a language like Forth, it becomes very easy to kind of just think about each argument as calling. You don't need to pass parameters, so compilation can be really simple. So if we had a C-like code where we had F, and then we just had some A, B, C, we can just do this as calling A, calling B, and calling C. And so we're going to actually show you how that's done. In this Forth model, there's 2 stacks to keep track of. There's a stack down here. This is called the parameter stack. And as you can see, as I'm typing things, it comes out and we can print it. This is called the parameter stack, but there's also a thing called a return stack. In this implementation, we are doing something special in that the EBP the base pointer is the return stack, and the ESP is the parameter stack. This is just kind of important to know because we're going to be having the ESI be the next word, and we're going to be a bit cheeky because we want an interpreter, we want a compiler that we can play with, but things need to keep going forward, right? And how we kind of keep things moving is through a word called next. All next does is load the ESI registry into EAX, and then we jump into EAX. So if ESI is the next instruction, then we just load that into EAX and jump there. It's really that simple. And to show you kind of what this looks like in practice, they give an example called quadruple, where you compile quadruple to be double, double. And as you can see here, you have the address of double when you're compiling the word quadruple. You have double twice, and then some word named exit. I'll get into what exit is later. And then, you have a code word named double, which is just do plus. It just adds it to itself, which makes sense, unlike my definition, which is square. But, as you can see here, if we just call, all we really need to do is, well, we get this instruction, right? We have the ESI here, and then we jump here, and then we just need to set up some things. This isn't perfect, but it works really well. To get a feeling of how to make it work is in that when we jump to a word, we get to save the old ESI. Because if we jump, we need to have a place to go back to. So all you really have to do is save the ESI in the return stack, and then when you call next, it pops it and jumps back, as we saw previously. And that's all that's all you really need to do to call a word. And so we usually append all words by a notion called do call, which pushes the ESI to the return stack. It adds for skipping over the word, and then we basically load it into the ESI. And so when next gets called, we just jump to it. And push and pop are just assembly macros that basically pop to the base pointer, because instead of using the stack like a normal language, we've kind of swapped them. So we get to make our own push and pop. But these are just the same push and pop in assembly as you know them. And so they kind of give an example here where the EAX is here, the ESI is here, and then we store, we just add forward to EAX, so we're on the address of dupe, we save the ESI for the return, and we go back. It's really all that simple. That's it. And now we should get more back into the layout of how this stuff works. As described before, there is a link here, which we can get at latest, and this can point to the previous word. This is some address, and you can keep getting addresses. This one isn't a good example because it's not exactly this, but nonetheless, the format's kind of like this, where you take a link, we get the name, and all that. And so I think they're setting up, they're setting up this. So this is the setup for our word. And so all they do is define an assembly macro. I don't really like AT&T syntax. It's rather abhorrent. So we're going to just use Intel syntax for demonstration purposes, and because I like it better. And I want label defcode. I want defcode. And so what we do is for something like defcode, we're just going to store the information. This is just an assembly macro to kind of store things. You can kind of just say, well, okay, we're going to have a global name. Just put the link. This is the latest. And we're going to just define link to be this. So we're just like overriding the definition with the new one. Much like in Haskell, we'd say like let x is equal to 3 and let x equal to 4. It's a new x, but we're just setting up a new link. Then we're setting its flags, like get into flags a bit later. You set up the name of the string, you align it, and then you just kind of set up the code. That's all def code really does, is that it just sets up this kind of link 3 dupe code dupe. So you can just start writing code here. So you can just start writing assembly, which is really nice. This isn't everything that you need. There's a thing called def word, which is very similar, except it calls do call, which, as we saw before, pushes the ESI into the return stack, so we can jump back to it. and that's like the only difference between a word defined in Forth. We will be using this to define Forth words, and words defined in our assembly is just the assembly is like microcoded, where we don't have to worry about it. And yeah, it's quite nice. And so they start defining some stuff because our normal stack, the parameter stack is the ESP. We can just use push and pop, and you can see we can just define drop as pop. It's literally a one-line instruction, which is very, very nice. I wonder if it's like that here. Yeah, not quite so simple in JonesForth, but if I have my location here, I think I can say C drop, and it doesn't tell me for primitives. What a shame. But either way, it's just pop EAX. Swap is you just pop two things off the stack and you push them, because you pop EAX, this thing on top, you pop EBX, that's the second thing, you push EAX, and then you push EBX, and this would just swap the two things on top of the stack, right? Like you just see that, ooh, they're swapped. Dupe is very simple. You just you move the top of the stack pointer to EAX, and then you push it, right? And these are all code words. Notice that each of these are defined by next, where next kind of just sets up the interpreter to keep going, because the only thing keeping our ship afloat is next. Next just basically says return and keep going. And this is vital, because if you don't say next, our entire machine stops and it will try to keep executing code after it, which wouldn't make sense. So this next is vital, that every word ends in next. And we just define most things. Like we are already halfway done with this compiler. Forth is that basic. Like you see, so these things are just defining some stuff in assembly. You don't have to. You can implement these in Forth. They just do so for efficiency reasons, which you could just ignore and just cut, because you can define it yourself. What we didn't show you is exit. So we said before that code word kind of would set things up, and next would jump back. However, next doesn't get off the ESI. It just kind of jumps. It assumes the ESI is set up properly. So all exit does is pop the ESI into our return stack, and then next just jumps to it. So it's really nice in that it just kind of sets up the environment for us, and it's just a single line of assembly. Great, we have word definition. We're done, effectively. There's some more details to set up, but we're effectively done. So you can kind of see the format, and I can actually prove to you. Well, I guess I'll get to literals. You can also push literals onto the stack, and some other things that are important is that you can write memory. So bang allows you to write memory, and at lets you reference memory. So if I have some address, I can use at to reference it. So if I have here is just the current place in the stack, and I can reference it with that, which, it's bound to 0, because there's nothing really there in this case. But I can also bind to it. So I can say here, and I can say 5, and I can bang, and now when I get it, 5 is now on the stack, because I set the memory location. And you can see that by me dumping assembly, and you can see that at this memory location we have 5. And we can also write characters, very useful. We can write strings. Now we're kind of getting to the fun stuff. Yeah, should I spoil the party? You're kind of seeing that I'm manipulating the environment here, but I want to kind of this stuff's kind of boring. This allows you to manipulate the return stack, but the real fun stuff, I guess, begins after this. First, let's talk about parsing. So we're already halfway done through our implementation. And now we just need to parse, because parsing is important, but parsing in Forth is easy, right? All words are just space separated. So, you read a key, and if the key is not spaced, you keep reading. So key, this bit of assembly right here, this right here, just reads a single digit. And then we can call emit, which, we define. What's great is that key is available in Forth because we use def code, in which we just call the labels. You can just view this as microcoding this assembly into our implementation. Our implementation does not have enough to support this, but if we, the VM writers, give it to the language. Now the language has the power of reading a character without any interference from anybody else. And emit just prints. And you can see it's really basic. It's not much. You're just like writing to a scratch buffer and then like dumping it. Yeah, it's not very sophisticated. And then finally we have Word. And all Word does is just parses a thing, and if it's space separated, well, then you're solid. Yeah. You know, and it's fairly great. Even 5 can be a word. So I can define 5. I can define 0 to be 1. So when I say 0, I get back 1. Because I can just define a word. It just parses as you would expect, and I can just define 0 to be 1. It's really cute. We also define what numbers are. We get hexadecimals by just setting a base parameter. So there's a thing called base. Actually, let's see. Hex. It just sets base to be 16, really. It just sets 16 to be the base. And we read this parameter, especially when we're parsing. It just compares that against the value getting in, and then we shift the numbers by A is 17, and so, you know, you just do the comparison and you get hexadecimals for free. It's really just, I don't know, 50 lines of code, and you will get hexadecimal and all that. Next up is find. I already told you about latest. From latest, you can just keep finding words, and find is wonderful. It just allows you to like look up a word. But some other fun things is we kind of want a pointer to the start of the word itself. So we have a thing called CFA, and CFA just gives me the pointer at location, and that's when I type triple like this, I'm getting the pointer to the CFA. That's why I have to do 8 cells minus, and then I dump. And then I dump like what, 12 cells? Let's dump 12 cells. And that's why you see here that triples here. Oh, it's like 4 cells minus, no, 5, it's 5. I didn't. Great, you can see that it's 5 cells minus, and you can see the names right here in the size. And so when we get that, we're just getting the CFA, you know, before it calls exit and all that. I think we can finally talk about the fun stuff. So, colon is a bit special, but not too special. So I've been defining words with colon, as I showed before. Like double was, you know, like that, and I can just share it again, or I can square. U is dupe times. You can define words with colon, but colon isn't special. And notice I can just type it here. What's really happening is as follows. There's 2 primitives going on. There's create and comma. So create just creates some space. So for example, I can say create foo, and now I have a variable called foo, and here is pointed at foo. It just placed a marker at here, and that's all create really does. It places a marker and, like, I think reserves some space. And comma allows us to dump information there. So if I say 1, 3, comma, now when I look at foo, so I dump, we can see that 3 is stored here. And here is incremented to be this location right here. So if I do 5, comma, and I get foo, and I get the address and I 16 dump it, we can see that we have 3 and 5. And so when I were to say do foo at, we get 3. And if we increment the address by a cell, we get back 5. That's all foo and comma does. And then finally, there's a thing called immediate and compile mode. So when we're running things like plus, this is immediate. We run the plus and it goes away. However, we can't do that in a definition, right? If we're doing this, I can't just run dupe. There's nothing on the stack for dupe to run on. So we have a thing called immediate mode, compile mode. And what colon does is turn the compiler into compile mode, and when the interpreter will get to later sees it, it'll look up the CFA of dupe, much like how I said dupe like that. And what's great is that from this, we have the CFA and we can just place it in memory, right? So I just have the address, which I think is fairly wonderful. And that's all you really need. And to prove to you that we're not doing any tricks, and the way that you control this is with brackets. So forward bracket turns it into immediate, and then right bracket turns it into compile. So to kind of prove to you this is the case, I'm going to make our own defining function. With the primitives we have now, I don't even need colon to be defined. They define colon right here. I don't need that garbage. We can just write it ourselves. So the first thing we do is probably, I'm just going to write some memory. I'm going to take here, and I'm just going to write the following. We know the format. We look at the format. Here, I want to get words, so I want to write down foo. So there's a little trick where I can just parse a string, and this will set up the name correctly. So I'm just going to comma, comma. So I'm going to just, when you write a string literally, get back two things. So I'm writing foo here. Now I need to write the do colon literal. So, we just do col, and then I comma it. G4's a bit special in that it requires some extra padding on my part. So this already sets up the length in the name. Then this sets up the do colon, but G4 is a bit special, and it needs, I think, fourth start. Start fourth. It's start fourth. I had to actually look this up. It took me a while to drive this by hand. Yeah, fourth start, and then I just need cells. I just need 4 cells. And then I want to write this memory address. I want to get the address of fourth start, add 4 cells to it, and then put it here. This is special. It took me a bit to derive this. I had to look at some assembly, or some of the dumps you saw, not assembly. But it was easy. I was able to derive it. Now we can put it into immediate mode, compile mode, which is left bracket, I believe. I believe it's right bracket. Yeah, it's going to look like this at the end. It looks kind of funky. And so, well, I want to write our definition we had before. So I want to write dupe. I actually want to write double. Let's dupe double times. I think that's a fine definition. We're going to basically implement our triple function previously. And I believe this is all correct. We still have to call exit, as you saw before. Exit's important. I'm pretty sure I need exit and not double. I'm just going to cheat here for a second. Yeah, I'm exit. Cool. And so now we have defined foo. Oh, wait. Whoops. I messed up. It should be exit comes before this. There we go. Much better. Much better. Now I want to set the last thing in the dictionary to be it. As mentioned, the last thing in the dictionary just points to the definitions in the word. Now that it's set, we can now say 5 foo, and we can see that I messed it up. What did I do? Okay, I'm going to cheat. What did I mess up? Oh, I forgot to place that.
By the way,
yeah.
I'm curious, is that some weird Emacs mode or something that you have there?
Down at the bottom here?
In the actual fourth thing, yeah.
No, this is just G4.
Huh. That's pretty interesting. My G4 does not have fancy cards and so on.
You should get the latest version from the actual website. It's nicer.
I see.
Yeah. Let's see. Oh god, did I paste it in right? I didn't paste it in right. There you go. Yeah. Sorry. Sorry for the anticlimactic undefined word. It was just working a second ago. 1 second. Yeah, that did include 1 second. Presentation.fs. Okay, there we go. Great. Now we have it 5 foo, and we can see that it says undefined word. Why? This should be right, unless this was the one I didn't define properly. I think that's the one I didn't define properly. I'm just going to use this one. Yeah, sorry for the anticlimactic. It works. Woo. I used a slightly different one with create, as they showed there. This derivation isn't much different from this derivation. I apologize for some sleight of hand. But it basically is just placing the variables there. In this case, I just allocate a bit too much, and then I offset it. But as you can see, we're just following directly from the implementation here, making our own colon definition. If you were to intersperse it with compile time a bit better, you can actually make a colon definition and make your own word compiler. Note that this is the entirety of compilation. We're done. And you could extend the compiler by defining out your own colon. that runs a CFG graph and optimizes if you really want. There's two things on Unix. There's JonesForth and JonesForth-fast. But since I only believe in debug mode, I don't use the fast version. And yeah, that's all really the implementation has. There's notes where we hide definitions, but we're essentially done. We've gotten into the main meat. There's just a few primitives left, like branching. There's just branching and quitting. But the last high triumphant thing is the interpreter. This interpreter is special. We saw our first interpreter with do call and next. Next just jumps to the next instruction, and that is an interpreter, right? It just keeps making the instruction pointer go brr, right? It just keeps going in a loop. It's beautiful. But what is special about this interpreter is that we're essentially using the VM that we've written to propel almost an interpret word in Forth itself. It's not quite in Forth, but we're essentially adding it to the language. And we actually do, this is def code. When we see def code, this means it's Forth code, but we're just putting it in here, and we're doing some assembly in between. But it turns out to be the same, and all this interpreter does is we parse a word like 55555. It checks, is it in interpreter or compile mode? If it's in interpreter mode, it runs it, which just pushes 5555 as a literal in place. If it sees a word like double, it searches the dictionary, and it just runs, right? So that's kind of nice. It just kind of looks at the dictionary, it finds the word, it finds the CFG, and then it just jumps to it, right? You can imagine how it's implemented. It's only, how many lines of assembly? I think it's only, this is like the biggest function in here, but it's not that bad. It's about 80 lines of code to do all that. If it's in compile mode, it just then looks up the CFG and writes it directly, much like we were doing here. It just writes it directly. If I could have just done dupe and comma, and then when I look at here, if we do cell minus, and then we dump 16, we can see that this is the address of dupe, basically. Dupe x dot decimal. You can see that this is it, 7F, 3E, OF, AO, OD, 10. And you can see that it literally just writes it at that spot, which you can implement this yourself, and we're done. They do some other things like syscalls, because you do want to be able to call C. It is very helpful to be able to call C. And then the rest of the language, ifs and everything else, is defined in Forth. You can define if, you can define not, you can define case. You have a very rich language at this point, and you can write anything you want. It is more, you have more power than you do with C. You have more power than you do with ML. You have more power than you do with a lot of algoloics. You can just do whatever. You can see that I can just write in the raw Forth basically my own colon word, and just write the memory address myself. I don't even need to go through like the standard APIs if I understand the base layout. And all this code just gives us the standard library at that point, which I think is rather oppressive. So like half the implementation is Forth, like for half, because this has less comments in the assembly. So in reality, there's more Forth code than assembly code in creating this language. And I think it's quite beautiful. Like this if else then, you can just derive it from the memory writers that you have. It's free. It's just free, and you can write fun things. Like I wrote a VM implementation. I wrote my own VM implementation of writing a little just stack-based language with stacks and like pushing things. And I would say it's a much more pleasant experience than doing it with C. It took me longer because I'm not used to writing a Forth-like language without brackets and closures. But you get case. Like I could do case here. And if I really wanted to, I can implement exhaustion if I so cared. Though I think a Forther would disapprove of such ideas, you can just do it. And so I even write my own hello world in my VM here, and then I have an entry code for running it, which I find very cute. And I can just like allocate memory and dump it, and I basically have a nice language to do anything I want. And you can bootstrap this in 500 lines of assembly, and then from this you can make yourself a Lisp, and probably about a couple thousand lines of Forth, if not less, if you do your compiler correctly. You can just keep going up the generation of languages. And I think that's quite special. I haven't found something as elegant at a low level kind of extensibility as like Forth here. I really do think it's like special in this kind of thing.
Yeah. A lot of what Forth ends up being used for is someone has a weird oddball CPU that they need to program to do something, and so they will write a small Forth in assembly, and then write things in Forth.
Yeah, it's a perfect second generation language. If you think of assembly as a first generation language, you then write assembly Forth on top of that easily, and then you have a really expressive language. You even get variables. This is a macro for local variables. You can just add variables to your language because it's easy. You have total control to do that. But yeah, usually Forth is used for operating systems. It's used to defuse bombs in real life. It's used for your washing machines. At least it used to be. It had a very interesting lifespan, and there was hypothetical machines around it, and I'm sure it probably inspired the SecD machines and most of the abstract machines that we end up using today, at least for compilers. So I think it's very, very special, language wise. Does anyone have any like questions about the implementation or things you can do with it? I kind of went over it really fast, but like you can just like write memory, and that becomes very special because you have a REPL over memory. Like when I was trying to debug things, I found it invaluable to just dump memory locations. Like I had some things here. I want to include the presentation again, where I would just dump like say the word of double, and I would just look at these bytes where I can see where this is literally written, and then I was able to reverse engineer the fact that this looks like do call. I just know this memory address that this is start address plus that because I can just type it. I can just say 7F 69 70 40 36 28, and then I can do decimal. And you can see it says Forth start plus 20 because this environment is very helpful. And I can do further things like see Forth start if I'm curious what it is. That's not that helpful. It just tells me that it gets some image header. But I can also ask for help, and it can look it up in the source code because it saves this kind of information. And all this is implemented in Forth from the primitives you see there. This is derivable, right? You can just derive all this. And yeah, stack-based languages are very nice for getting things done like this. Cool. Yeah. Yeah, I always like this trick where you can just define words yourself. Again, if you know the format, you can do things. Forth, one interesting thing about Forthers is that they hate standards. Forth should be case sensitive, but since people disregard standards in Forth quite often, words aren't necessarily case sensitive. There's a lot of interesting things where there's extensions where if can be used in immediate words. The way if is compiled, it only works in compiled words, sadly, at least in JonesForth and JonesForth, but it's left as a exercise for the reader to implement if as a word that works both in interpreter and compile mode. Some other interesting things, all words are early bound. So if I were to define like dupe and then define a function on dupe, and then change dupe, all functions using dupe don't get changed because you have like a list of functions being defined. As you can tell by the latest, you just traverse your own list. But what's interesting is that you can make late bind. All you have to do is instead of placing the CFA of the word that is there, when you're compiling, you simply defer it to a hash table lookup at runtime. And from there you can get pretty fast dispatch, but you can get late binding into Forth. And you can just do that. I don't know, I find that really dope. You can't do that with C, C is a very large language, not close to this computer at all. But this is like right on top of the assembly. It's much closer to any type of machine than C is to its abstract machine.
I think what Forth people do in practice is they have all rolled their own Forth, because it's not really much code to roll your own Forth.
Yeah, effectively. I know the guy who made Forth took more. He had some interesting Forths. Like he made color Forth, where instead of using syntax, he used colors to denote ending syntax, which I thought was really cool. That you can just use colors to denote syntax. I found that really neat. But yeah, usually you can just roll your own, especially if you're writing your own CPU or writing something on like base hardware. It's very useful. There's a good story about three-fourths make a whole, where these people are defusing bombs with Forth, and it's really great because if you have buggy hardware, you can intercept it with Forth because you can like ask Forth questions about the underlying machinery, and if you build words around it, you end up getting really nice visual displays. Um, so it turns out to be very useful in real world scenarios. It's not just a toy language. Cool. With that, I will call the video a do.